Hello, today I'll be explaining transformations. By the end of this video, you'll know how to move the graphs left, right, up, down, how to dilate them, and how to reflect them across any axis as well. So let's start with moving graphs left and right. On the right hand side here, you can see how we have a parabola. Now, what would we do if we needed to move this 2 to the right? What if we wanted to move it 2 to the left? Well, I'll show you now. So let me write the equation of our parabola. If I wanted to move this 2 units to the right from the original, so this is the original position here. If I wanted to move it 2 units to the right, what I would write is y equals x minus 2 squared. So what I did was I replaced the x value. So you replace the x value with x minus 2. If I wanted to move it 2 units to the left, so from here, I wanted it to go here, it would become x plus 2 wherever I have an x. So it'll be here if I wanted to move it 2 units left. It would be y equals x plus 2 squared. So a lot of students may say, well, if I'm moving this 2 units to the right, why would it be x minus 2 in there? Shouldn't it be x plus 2? Well, I'll explain it to you like this. If we wanted to find the y value when x equals 4 in our original graph, we would get y equals 16. Now, in our graph where we moved it 2 units to the right, in order to get y equals 16 again, you need to put in x equals 6. That gives you y equals 16. So you can see how our graph has been delayed by 2 units. When y equals 16 normally happens at x equals 4, it now happens 2 units later at x equals 6. So that's why the graph essentially gets delayed. And if it's getting delayed, it's happening at a later x value. So you can see how it's getting moved to the right because of that delay. Now, when it's x plus 2, you're making the graph come earlier because you're making the values reach the same y value quicker. So I'll do that as an example as well. So in this example here, if we compare it to the original here, when x equals 4, y equals 16. In this one, all you need to do is put x equals 2 and you'll get y equals 16 again. So you can see how it happens at an earlier x value to get the same y value. So if it's happening at an earlier x value, you've moved the graph left to make it happen earlier. I hope that makes sense. Now, when it comes to graphs that are a little bit more complicated and have more x values, I'll show you what happens. If we had something like this, for example, if I wanted to move this 1 unit to the right, so move 1 unit right, all you do is replace each x value with x minus 1. So that becomes and it's really important that you replace every single x value with x minus 1. You can't just do it to this one or this one only and then expect it to work. It needs to be to every single one. So I'll do another example of a really hard looking graph, one that you might not even know, and show you how to move it left and right as well. So imagine I had y equals cos of x, and it doesn't matter if you know what this graph looks like. It really doesn't matter at all. Okay, so if I wanted to move this 3 units left, all you do again is just replace every single x value with x plus 3. Okay, so you're going to get y equals cos x plus 3 e x plus 3 plus sine, leave the 2 there, and then x plus 3 where that other x was. So I hope you can really see how all you do is replace the x value with x plus or minus whatever number you want to move it by. The next part is super easy. So imagine we wanted to move this parabola from here 2 units up. What would we do? Well, looking at our original, all you do is add 2 to the end. Okay, if I wanted to move it 2 units down from the original, so from here, I wanted it to go here, all I would do is y equals x squared minus 2. So whatever number you want to move it up by, you just plus that number onto it. Whatever number you want to move it down by, you just minus it by that number. It's really important to understand that it's not the opposite here. So when we're dealing with the x values and moving the graph left and right, it is the opposite. So if you want to move it left by 2, you need to write x plus 2 wherever you see an x value. But in this case, it's just exactly whatever you want to move it by. And it's always just on the end of the graph. So if I had a graph like this, something that you don't need to know what it looks like. If I wanted to move this graph up by 1, that's all you do. If I wanted to move it up by 2, that's all you do. If I wanted to move it down by 5, that is all you do. Now I'll show you how to dilate graphs. And what dilate means is essentially just means stretch the graph. So if we have a look at this parabola, if I wanted to stretch it upwards, I could get something like this. Okay, and I'll show you what happened. So if we look at our original parabola, we have a coordinate here. This is 2, 4. Let's see what happened to that coordinate in our new stretched graph. That coordinate is now 2, 8. So I hope you can see how the y value has been doubled. It's been doubled. So we call that a dilation of factor 2. And it's from the x-axis. And the reason it's from the x-axis is because look at the direction of where this coordinate has gone. It's gone up. It has gone up. And that's away from the x-axis, because if you trace it back, it takes you to the x-axis. So if we're stretching the graph up, it's always from the x-axis. And the good thing here is, if we're doubling the y values, it's a dilation of 2. If we're tripling it, it's a dilation of 3. If we're halving it, it's a dilation of a half. So whatever you're actually doing is the number that's written down. So it's really easy when it's affecting the y values. You probably noticed this with moving the graph up and down as well. That's also affecting the y values. And it's also exactly whatever number you're moving it up and down by. It's not the opposite, like with the x's. We'll get to dilating from the y-axis, so affecting the x's, in a bit. So what our graph would become here is y equals x squared is our original. When we apply this transformation, we get y equals 2x squared. So it's very easy. You just multiply the entire equation by whatever number you want to dilate by. So if I wanted to triple all of the y values, I would get a dilation of factor 3 from the x-axis, and that would become this. Okay, so if I had an example like this, and it said dilate by factor 1/2 from the x-axis, again, you would just multiply the entire equation by a half. So that would look something like this. You'll just put a half in front, and that's it. You can expand this. You can definitely expand this. I hope you can see how once you've expanded it, you get this half that's been distributed to every single number in that equation. Okay, so that's all you do. Multiply every single number in that equation by the dilation factor that you want. Now I'll show you what happens when we stretch the graph horizontally, so this way. Okay, so before we did it upwards, now we're doing it horizontally. So let's look at one of the coordinates again. If we have this coordinate here, 2, 4, and we compress it inwards like that, this becomes 1, 4. Now, what that's called is a dilation of factor half, because we've halved the x value, from the y-axis. So it's really important to look at the direction that the coordinate has changed. You can see that it's happening in that direction, and that's traced back to the y-axis. So it's from the y-axis. Now, similar to when we're stretching it upwards, whatever you're doing to that number, so we're halving it, that's what you write down here. But when we apply it to the actual graph itself, it's a bit different when it's affecting the x values like we see here. So our original graph is y equals x squared. What happens when you dilate by a factor of something from the y-axis is you write down the reciprocal of that factor. And reciprocal just means the flipped version. So you replace the x values with 2x. Okay, so in this case, where we have y equals x squared, it becomes y equals 2x squared. So you can see how I've put in the reciprocal of our dilation factor into there, and that would compress the graph. Okay. Now, if I wanted to dilate by a factor of 2 from the y-axis, so imagine I wanted this coordinate here to become 4. So I wanted the graph stretched out there. What I would do is replace our x value with a half x squared. And that will dilate by a factor of 2. So I hope you can see the pattern in that when we affect the x values, similar to when we move it left and right, it's a bit weird. So when you're moving it left and right, it's the opposite sign. So if you're moving it right by 2, it's x minus 2. And in this case, it's always the flipped of whatever factor you want to dilate by. Okay, so if I want to double this, you still write dilation of factor 2, but you replace every single x value with a half x. And I'll show you with a more complex example as well. So imagine I had a graph like this. And I want to dilate this by a factor of a third from the y-axis. So what that is physically doing to the graph is compressing it. So it is compressing it horizontally. It's not stretching it out, it's compressing it. But what you write down is this: y equals 3x, wherever you see an x. Okay, that's all you do. I hope that makes sense. And again, you may ask, why would you put in 2x when you want to dilate by a factor of a half? Shouldn't you put in a half x, right? Well, let's think of it like this again. So let's look at our example from up here. I'll copy it down here and I'll show you. So this is really similar to when we were moving it left and right. It delays the graph. So if I had x equals 2 here, that would give me y equals 4. Okay. In this case, all you need to do is you put in x equals 1 and you'll get 4. So you can see how that 2 has made it so our graph is a bit earlier. So in this case, it makes it come earlier. So instead of it being stretched out coming later, it's compressed and coming earlier. Now, before I did mention how it can delay a graph, and I'll show you how it delays it as well. So when I want to dilate by a factor of 2, like we have here, I put in a half x. Let's show you that example as well. So if I have the original, remember in words, this is dilate by factor 2 from the y-axis. So physically, this is stretching the graph out. It is making it fatter. It's going out this way. Okay. Now, why would you put a half in there? Well, let's do an example. So if I pick x equals 4 and we try and find the y value, you'll get 16 in the original. In our new one, to get the same y value, you need to put in, x equals 8. When you put in x equals 8, you'll get y equals 16. So you can see how much our graph has been delayed by. It's been delayed by a fair amount. So instead of it being compressed, it happens later. So it gets delayed, and the same y value happens at a later x value. Some of you that were looking out may have said, wait a minute, you're saying this is stretching the graph this way, but what if you just looked at it from a different coordinate? What if we looked at this one here, 1, 1, and then said, wait a minute, that becomes 1, 4. Isn't that dilating by a factor of 4 from the x-axis? Well, let's have a look. Looking at the previous transformation that we applied, we said that we dilated by a factor of a half from the y-axis, and we applied it by replacing the x values with 2x. Well, look what happens when we expand this equation. We get 4x squared. If you remember from before, I said that when you dilate by a factor of something from the x-axis, you just multiply the entire equation by that number. And here you can see how our original graph has essentially been multiplied by 4. And that's a dilation of factor 4 from the x-axis. So what this shows us is that you can write a dilation from the x-axis and from the y-axis using different numbers, and by doing one dilation, you're essentially doing another one at the same time. Okay, so I'll give you another example. So imagine we had y equals root x. Okay, and I wanted to dilate this by a factor of 4 from the y-axis. So this is physically stretching the graph out horizontally. The way you apply it is by replacing the x value with 1 on 4 x. So you can see how we get this. 1 on 4x. Now, if I took that out of the square root, you could take it out by writing it like this. Square root 1 on 4 times square root of x. And what that leaves you with is a half at the front with your x like that. So you can see how this is the same thing as a dilation of factor of a half from the x-axis. So both of those transformations lead to the same result. It just depends on which perspective you look at it from. Let's have a look at reflections across the x-axis as well. So when you reflect across the x-axis, you're mirroring it across. And let's have a look at one of the coordinates to see what's happening. So if we look at this coordinate, this is 2, 4. What does it become when we reflect it? Well, it becomes 2, negative 4. I hope you can notice that the x value doesn't change, but the y value does. So what happens to our graph is all you do is you times the whole thing by -1. Timesing the whole thing by -1 gets you a negative at the front, and it flips it across the x-axis. So whenever you want to reflect any graph across the x-axis, you just multiply the entire thing by -1 to make all of the y values negative. So I'll give you another example. So imagine we had something like this. All you do to reflect it across the x-axis is multiply the whole thing by -1. And then you can expand it, and you'll get this. So you can see how that negative has been applied to all of the terms in this graph. And finally, I'll show you how to reflect across the y-axis here. So reflecting it across the y-axis makes it a mirror image across this vertical line. Now, if we try and apply this to our parabola here, and we try to reflect it across that line, I hope you see that it's symmetrical. So flipping it won't even do anything. I'll still show you how to apply it to this and show you why it doesn't do anything as well. So what you do is, you replace all x values with negative x. And you can see with this example here, if I look at this coordinate here, 2, whoops, that's not 2, that's 4, 2. When I reflect it, that becomes negative 4, 2. So you can see how the x is a negative. So that's why we replace all the x values with a negative. And if we do it with our first example here, our parabola, this is what we get. We get y equals negative x inside. And when you square that and you take it out of that bracket, you're left with x squared. So it hasn't changed anything at all. But I'll show you our example here. So our graph on the right, the white one here, that one is root x. When we reflect this across the y-axis, it becomes, I'll show you here, you just replace your x value with negative x. So you can see how that's what you get. So if I had a more complicated graph, something like this, and I wanted to reflect this across the y-axis, again, all you would do is replace every single x value with negative x. And that will do your reflection. Here is a summary of everything that I talked about in this video. Take a photo of it and make yourself really familiar with it before you move on. So I'll explain everything step by step to make everything make a lot of sense as well. So I'm using this graph as an example, and you can see how I've color-coded everything, making the red horizontal transformations, so ones that affect x values, and the green vertical transformations, so ones that affect y values. And I've used the number 2 as our transformation just to keep everything consistent, but you can use any number. So translating a graph left by 2 means that you replace every x value with x plus 2. Translating a graph right by 2 means that you replace every x value with x minus 2. Dilating by a factor of 2 from the y-axis means that you're still physically stretching the graph horizontally, so you're doubling the x values, but to apply this, you replace every x value with a half times x. Then reflecting across the y-axis, you just replace every x value with negative x. Now moving on to vertical transformations, to translate a graph up by 2, all you do is add 2 to the end of our graph. To translate a graph down by 2, you just minus 2 from the end of the graph. Then when you dilate by a factor of 2 from the x-axis, remember physically this is stretching our graph upwards, so it is doubling all of our y values. And what you do is you multiply the entire graph by 2, as you can see here, and there's brackets here. Remember that, because you're multiplying the whole graph by that number. Then finally, reflecting across the x-axis, you multiply the entire graph by a negative 1, and you can see the brackets here as well. I also want to show you how to apply the transformations that I just taught you using function notation. So just a little refresher, I hope everyone remembers that if you write f of 2, for example, that just means that you replace every single x value with a 2. So you'll do this. And this will work out to 4 plus 4, which is 8. So remember that whatever you put inside of this bracket here, you replace every single x value with that number. So you can use this when you're transforming as well. So remember at the start how I said that if you wanted to move our graph, for example, to the right by 2, I hope you remember that I said you replace every single x value with x minus 2. So you can write that like this. And you'll get this. Okay, so you apply it the exact same way that I showed you before. I'm just showing you this because sometimes they may show you this right here and they might say what transformation is that. So as long as you know that means that you're replacing every x value with x minus 2, you'll be able to say that it's moving the graph to the right by 2. We can apply our other transformations as well. So I hope you remember that I said you add a number to the end or you minus it when you want to move the graph up and down. So for example, if I wanted to move our graph up by 1, you just add 1 to the end of it. If I wanted to move it down by 2, you just take away 2 from the end. I hope you also remember how we did our dilations. Do you remember that you multiply the whole graph by a number when you're dilating from the x-axis? Dilate by a factor 2 from the x-axis. That's a vertical stretch of our graph, and you apply that by just multiplying f of x by 2. And I hope you also remember that when you dilate by a factor of 2 from the y-axis, that is affecting our x values. It's a horizontal stretch, and the way you apply it is by subbing in a half x into every single x value that you see. So for this example, we would get this. As our answer. And when we reflect our graph, so if I wanted to reflect it across the y-axis, remember that's affecting our x values, so you replace every x value with negative x, and that reflects it across the y-axis. If you want to reflect across the x-axis, so if you wanted to do it across the x-axis, then you just multiply the entire graph by a negative. So you can just put the negative at the front like this, and that will reflect across the x-axis. I also want to show you something called mapping notation. This is just a different way of communicating to you what transformation they want you to do without using words. So you can see here in our first line, it says translate 2 units to the right. Now, instead of writing this in words, you can use mapping notation to explain the same transformation. So what you can see on the right here is x dash. This means new x coordinate, and this is our old x coordinate here. And what we're doing to our old one is just adding 2. So you can see how what's written here is physically what we're doing to the coordinate, and it's the same thing as what we write in words. The way you apply it though is still the same way that I explained to you before. So you would still apply it by replacing every single x value with x minus 2. And you would get this. Okay, so that's really important to understand. A lot of students get this mixed up, but whatever is written here is what is written in words and is physically happening to the graph. So you can see with this second example, it says translate 2 units to the left. So it's physically moving it 2 units to the left, and it's 3 units up. So you can see how it's just our old y coordinate plus 3 gets our new y coordinate. And the way you apply that to our graph that we have above is like this. So you move it 2 units left by replacing every single x value with x plus 2. And then you move it up by 3 by adding 3 at the end. Our next example, it says dilate by a factor 2 from the y-axis and translate left by 3. So when you dilate by a factor of 2 from the y-axis, you're physically stretching the graph horizontally. So you can see how our old x value is being doubled, and then we're minusing 3, so we're moving it left by 3. So the way you apply this is exactly how I showed you before as well. So to dilate by a factor of 2 from the y-axis, you replace every single x value with a half x. And then left by 3 is when you then replace every single x value by x plus 3. So you can see how now I will locate each one of the x values and replace it with x plus 3. And then you can expand this and simplify it, but that is how you apply it. So this might be the first time when you've seen me apply something to the x's and then apply something again to it. It's important not to get confused because you just apply the same rules. As long as you keep that consistent, you won't get it wrong. Our last example here says dilate by a factor of a half from the y-axis and factor 3 from the x-axis. So dilating by a factor of a half from the y-axis means that you are compressing the graph horizontally, and to apply this, you replace every x value with 2x. So you get this. And then dilating by a factor of 3 from the x-axis means that you're stretching the graph up vertically and you're tripling all of the y values. And to apply this, you multiply the whole graph by 3. So you would just get this entire graph times 3. And you can expand that and simplify it further as well. Here we have a practice problem. Let's apply these transformations step by step. So first it wants us to reflect in the x-axis. To apply this, you multiply the entire graph by -1, and that gets you this. So that's our first transformation complete. But we need to do them all back to back. So next we need to dilate by a factor of a third from the y-axis. Now this is affecting the x values. It's compressing the graph. And the way you apply this is you replace every x value with 3x. So we are going to have, following from the transformation we just did, replace our x with 3x. And you can expand it here just to make it cleaner. And that's what we have there. Then it says translate 1 unit in the positive x direction. So this is 1 unit to the right. And the way you apply this is you replace every x value with x minus 1. So you'll get this. And when we expand this, we get y equals negative root 9x minus 9 minus 2, and minus 9 minus 2 is equal to negative 11. So that would be our final answer. Sometimes you might come across a question like this, where instead of writing the transformations in words, they give it to you using this notation. And I explained that before. This is just a substitute for the words. So whatever is written here is what is happening to the graph. So here it says x plus 3, you're moving the graph 3 to the right. Here you can see that there's a negative, and that's affecting the y values, so that's reflecting across the x-axis. Here's a 2, which means you're doubling your y values, so it's a dilation of 2 from the x-axis. And then here we have a plus 1, and this is adding 1 to our y values, so it's moving our graph up by 1. And we can apply these transformations one by one. So let's start with the x's first. So let's do our first one. It says move 3 to the right. So to apply this, all you do is replace our x values with x minus 3. Once we've done that, we can expand this and make it look cleaner. And we get that. Next it says reflect across the x-axis. And to do that, you multiply all the y values, or you multiply the entire equation by a negative. So that gets you negative here. and this becomes a negative as well, and this becomes a positive when you multiply by a negative. So that's all done. Next, we have a dilation of factor 2 from the x-axis, and to apply that, you multiply the entire equation by 2. So that gets us a 2 here, which you can write at the top here. This becomes a 4 when you multiply it by 2, and this becomes a 12 when you multiply it by 2. Then finally, we need to move it up by 1. And to do this, all you do is add 1 to the end of this. And when you combine these two, you get 13. So this is our final answer. Sometimes you might come across a question where they ask you to write down the transformations that have been done. So I'll go through this example now. Now there's a trick that you need to do that makes this much easier. And that's whenever there's a number in front of the x, factor that out first before you start comparing the transformations. So factor that 5 out and you'll get this. Now we can use the acronym DIRT to know the order that we can do these transformations in. This is dilation, reflections, and then translations. But as you do this, it will become more natural as to what we need to look for first. So to get from root x to this, we need to get a 5 in there first. And the way to do that is to replace x with 5x. So replacing x with 5x means that you dilate by a factor of 1/5 from the y-axis. So when you apply that, you apply it as writing 5x wherever you see x. Now that we've done that, we need to replace x with x minus 2 on 5. And what that is it's a translation of 2 on 5 units to the right. And you apply that by replacing every x value with x minus 2 on 5. And now you can see how we got the same answer here, which is the same as our original. Thank you all for watching. Email me for any tutoring requests and comment down below if you found this video helpful.